Hello everyone. In this video, we're going to cover chapter 12, section 12.7, where we're going to look at motions, motions of a particle that's not on a straight line. Normally, curvilinear motion, when the particle is not moving on a straight line, we're going to break our motion into two components in 2D. So in the past, right? 2D motions, a lot of times, say projectile motion, for example, we are breaking it into the x-axis, y-axis, right? Horizontal and vertical. But in the curvilinear motion, a lot of times we break it into the normal direction and the tangent direction. So in the n, so in the n direction, and n stands for normal, and then the t stands for tangential. So two different coordinates are often used. And then just keep in mind that positive and t directions are defined by the unit vector un and ut. Center of the curvature O always lies on the concave side of the curvature. And the radius of the curve rho is defined as the perpendicular distance from the curve to the center of the curvature at that point. And the position of the particle at any instant is defined by the distance s along the curve from the fixed reference point. Keep going over here. We have our center. Keep in mind that center is where the concave side of the curvature, center O. Okay, velocity vector is always tangent to the path of the motion. That's what we define as the t direction. So in other words, the tangent direction, the t direction, will be at that moment, at that specific moment, tangent to the curve. Okay, tangent to the path of the curve of the path. And then magnitude is defined by taking the time derivative of the path. So v equals v ut. So over here, I know it looks a little funny. What it's trying to say is v equals the derivative of the position factor. Derivative of the position factor. Okay. And then having the v as defined as the magnitude of the velocity or the speed, we call it the speed. And then the ut defines the direction of the velocity vector. And then acceleration over here, acceleration, oh, by the way, this funny looking right here, on the previous video, we talked about they have a little G on top of it. That means a dot. So this one, it's got the and sign. So this, what it's trying to write is S equals S dot. S dot, derivative of the position vector equals, that's a dot. I'm trying to write there. Okay. There's a position vector derivative that is ds dt, ds over dt, derivative of position vector with respect to time. Okay, that's what it's trying to say it over here. And also in your acceleration, you will have taking the derivative with respect to time. And we know that this, what is trying the funny looking here, keep in mind that the and sign would just be a dot on top of it. So it will be v derivative of v, and then ut, and then over here, that's going to be v without the dot. And then this is going to be the ut dot. Okay, it's a product rule. So over here, v dot represents the change in the magnitude of the velocity. And then ut dot represents the rate of change in the direction of the ut. And then mathematically, after we break them down, the acceleration vector can be expressed in two parts: tangent part of the acceleration and then the normal part of the acceleration. Tangent part will be along the ut direction, normal part will be along the un direction. Now keep in mind that an along the normal direction, which is perpendicular to the curve of the travel, magnitude is going to be v squared over rho, v squared rho divided by the radius. And then the tangent direction, along the tangent direction, that is just going to be the magnitude change. Magnitude, so it will be derivative of the velocity. Okay, high level, what it's saying, very importantly, that's high level. What this section is talking about, acceleration, very importantly. Acceleration, we got two parts: tangent direction of the acceleration and then the normal direction of the acceleration. Tangent direction of the acceleration changes the magnitude of the velocity. So in other words, tangent direction of the acceleration, it's making the particle to move faster or slower, changing the speed. Normal direction of the acceleration is going to be perpendicular to the velocity. Perpendicular to the velocity means I'm changing the direction. Okay, tangent changes the magnitude. Normal direction acceleration changes the direction and magnitude. Okay, so tangent component is the tangent to the curve in the direction increasing, tangent component right here in the direction of the velocity. So tangent component changes the magnitude of the velocity, and then the normal component is how we calculating. It will be velocity divided by the rho, which is the radius of the curvature that changes direction. And overall, we use the uh, Pythagorean theorem that gives us square root of an squared plus at squared. Now, two special cases. Under the condition that we travel along the straight line, if we're traveling along the straight line, rho becomes infinity. We have this infinite big of a radius. Radius of the curvature becomes infinitely big. That means we're traveling along the straight line. In normal direction, normal component of the acceleration, v squared divided by rho. If the rho goes to infinity, that means an will be a zero. That means the overall acceleration total will be only the tangent component. That means if I'm traveling on a straight line, the only acceleration you will have is the same direction as the velocity. That means that acceleration will only changes the magnitude of the velocity. And then secondly, if the particle travels along the curve, if I'm curved like a circle, changing just a circle, only no horizontal, no tangent component at all. If I'm just traveling along the circle with a constant speed, that means all of my acceleration is doing the job to changes the direction of the velocity. Okay, so under that condition, all of the acceleration will be the normal component, which will be v squared over rho. Tangent component of the acceleration is constant. Under the condition that tangent component of the acceleration is constant, you have at equals at constant. And this goes back to our master equation, that we look at it for the past several videos. Constant acceleration, we can plug in into these three equations relating the acceleration, velocity, distance, etc. And then the particle, if it's moving on a path, expressed as y equals f of x, and then the radius of curvature rho at any point can be defined using this equation down at the bottom. Now, under the condition, if it's a 3D motion, the previous several we've been talking about right now, it's only 2D. This one right here, 3D motion, if a particle moves along the space curve, the t-axis is defined as before. At any point, the t-axis is tangent to the path, and the n-axis points toward the center of curvature. The plane containing the t-axis is called the osculate plane. The third axis can be defined. We'll call this the binomial axis, the B. Binomial unit vector UB is perpendicular to the osculating plane, and its sense is defined by the cross product UB equals UT cross UN, cross product. There's no motion, thus no velocity or acceleration in the binomial direction. Let's take a look at some examples. This one says a car travels along the road with a speed v equals to s, where s is in meters, rho equals 50 meters. Magnitude of the car's acceleration s equals 10. We're going to calculate the velocity when s equals 10 meters using vs. We're going to also need to calculate the tangent component and normal component of the acceleration, then the magnitude of the acceleration overall. We know that v equals 2s. When x equals 10 meters, that's what we're looking for. Under the condition that s equals 10 meters, we're going to plot it in, right? That gives us a velocity, plug in here, that gives us a velocity equals 20 meters per second. We know that acceleration, we're breaking into two parts, tangent part and the normal part. Tangent part would just be simply taking the derivative of velocity with respect to time. And therefore, we have 2v. So v equals 2s. We did taking the derivative of the velocity with respect to time. We got 2v. And we plug in the value v equals 20. V equals 20 comes out from when s equals 10, right? V equals 20, we calculate it. So the tangent component of the acceleration is 40 meters per second. And then the normal component of the acceleration is v squared over rho. There, my v squared is 20. Okay, v squared is 20 squared, right? Velocity, we plug in 20. And then the rho will be the radius of curvature, which is given in our problem. Rho equals 50. Plug in the 50. That gives us 80 meters per second squared. Now we have the normal component of the acceleration. We also have the the first one, tangent component of the acceleration and the normal component of acceleration together, putting into our Pythagorean theorem. That's going to give us the magnitude of the acceleration overall, which is 40.8 meters per second squared. We have tangent component, normal component, and then it's not the algebraic addition. They are perpendicular to each other. Vectors got directions. So overall, it's the diagonal of the normal and the tangent component together. Second example says the boat is traveling in a circular path. We know the radius of curvature is 40 meters. We know that a speed that is increasing with time, velocity equals 0.02 0.0625 t squared. We're looking for the magnitude of the boat of velocity and the acceleration at that instant t equals 10 seconds. So again, velocity is a function of time. Velocity is a function of time. We're looking for t at 10 seconds, right? Plug in the time t equals 10 seconds. That will give me the magnitude of the velocity at that 10 seconds. And then acceleration, two parts, again, two parts. First part is your tangent part. Tangent part will be the derivative of the velocity with respect to time. And again, plug in our time at 10 seconds. That will give me the velocity at 10 seconds, 1.25 meters per second squared. And then there's also the normal component. Normal component will be velocity squared divided by rho, radius of curvature. Velocity, we already know how much that is at 10 seconds, 6.25 squared. And then divided by down at the bottom, that will be of 40. Radius of curvature will be at 40, which is given in our problem. Rho equals 40 right here and right here. Okay, plug it in right there. That gives me the normal component of the acceleration, which is this much, 0.9766 meters per second square. Now again, they are two normal component and the tangent component. They are perpendicular to each other. We're taking the square and the square root of a n squared and then at squared. This gives me the magnitude overall, magnitude of the acceleration overall. Okay, last example right here. We have a train traveling along a curved direction, and this gives me a lot of information here. We know the speed is 20 meters per second, acceleration of 14 meters per second square, acting on the direction right here shown. We got a 75-degree right here. And then we're looking for the rate of increase in the train speed and the radius of curvature of the path. We know that the speed is 20 meters per second. We know the acceleration is 14 meters per second squared, acting on the direction 75 degree. Okay, so it's the acceleration overall we know, but we're looking for the speed of the train, the increase in the rate of increase in the train speed and the radius of curvature. So we're breaking our acceleration into two components. You have 14 meters per second square. Okay, so we do using that 75-degree, we're doing a sine and a cosine. We figure out the acceleration on the tangent direction and the acceleration on the normal direction. And we plug into our direction to our equation. We know that tangent direction of the acceleration will be the rate of change of the speed. So this number right here is the v dot, is how the magnitude of the change of the velocity. And then this number right here will be the normal component of the acceleration, which will be v squared over rho, which is the velocity, the 20 squared over rho. Okay, and knowing that this is 13.52, we can calculate the rho, the radius of curvature, which is 29.6. Okay, hope that helps you. So this one kind of goes a little backwards. We got another group problem right here. We starting from rest by we have somebody bicycle travel around the horizontal circular path. We know the radius of curvature at the speed of the at the speed of at the speed of at the speed. What this is repeating, sorry. At the speed. So we know that speed right here, velocity equals 0.09 t squared plus 0.1 t meters per second. We're looking for the magnitude of a velocity and acceleration when she travels 3 meters. We know that velocity is first derivative of the position. So if I know the equation for the velocity and if I taking the integral of that velocity, that will give me the equation for the position. We're going backwards, okay? So this is our equation for the position. Under the condition that we we know that this thing travels 3 meters. So in other words, we know the position. Okay, we're taking the integral of the velocity that gives me the function of the position with respect to time. And then if we plug in the actual the actual 3 meters, right? How much we travel, the position, 3 meters, plug it in. We can calculate the value of t. This is what we got for the value of t. And then once we get the value of t, plug back into the velocity equation, that will give me the velocity at that time. So, which is what we're looking for. We're looking for the magnitude of the velocity, right? At when we travel 3 meters, right? Using the velocity going backward integral to find the function of position with respect to time, and then we plug in the t. We solve for the t, right? Using that s equals 3 meters, and plug that t back into our velocity equation that give us how much velocity will be at that time. And then going forward, the derivative of the velocity will give me the acceleration. And look, we got two components again, tangent component and the normal component. Okay. And each one of them, tangent component will plug in the t, 4.147, getting from the previous slide. We get the tangent component of the acceleration, and then also v squared over rho. That gives me the normal component of that acceleration. And then using the Pythagorean theorem, we'll put them together. That gives me the acceleration overall. Okay, this is all I want to show you for this video. Hope you find things in here helpful. Thank you for watching.